Yesterday we compared our two types of projectile motion problems that we will see. In fact, we saw both types on our unit assignment that's due later today, and there's a very good chance that we'll see both types on our unit test on Thursday. Those two types looked like this. The first type, we had a ball, or it could be anything, like a person or a car or whatever, going off the edge of a horizontal roof or the horizontal cliff or something like that, following a parabolic path down to ground level. We say that it has an initial velocity, I don't know, maybe 20 meters per second, and it has a height of, 40 meters, let's say. And then it has an X displacement that you can see that goes from the edge of the cliff to where the ball or car or person or whatever it is lands. The second type of problem involving projectile motion that we have is a ball or whatever being launched at an angle of, 40 degrees, let's say, at a speed of, 10 meters. Actually, let's not go 40. Going to end up getting confused with that number there. Let's go 50 degrees, let's say, and let's go at a speed of, 15 meters per second. That also follows a parabolic path, although this time it's a full parabola as opposed to just a half parabola. It doesn't matter. Same shape, just more of it, that's all. In both cases, we're going to start off by analyzing the problem the exact same way, the x component and the y component. We're going to say v is equal to delta d over delta t for the x component, both times. V is equal to delta d over delta t. How can we use that equation for the x component? How can we use that first equation that we ever learned in physics for the x component? When is that equation valid? That's our group A equation, right? When is it valid? Santi?
When the velocity is constant.
Yeah, when the velocity is constant. And that means, in this case, horizontally the velocity is constant. If I was to draw my horizontal velocity wouldn't be changing. The horizontal velocity is constant throughout both of these problems because there's no force acting horizontally. We're ignoring air resistance, right? In the absence of air resistance, there are no forces acting horizontally, so there's nothing causing it to speed up or slow down horizontally. Constant velocity. But vertically, there is a force acting. We talked about this the first day we introduced this. It's gravity. Gravity acts down. Gravity is going to cause this thing speed up vertically as it comes down. The vertical velocity becomes bigger and bigger and bigger. And in this case, it actually becomes smaller as it goes higher up. But then when it reaches the peak height, what's the speed of it vertically when it reaches the peak height? 0, it stops, right? But then it starts speeding up again as it starts going back down the other side of the trajectory. So if we have, for the y component, acceleration, then we have to use a group B equation for the y component. And the group B equation that we're going to use is d is equal to VIT plus 1/2 AT squared. Now, the reason we're going to use that equation versus some other group B equation, they're all valid, right? But the reason we want to use this one rather than some other group B equation is because, for those of you in math class recognize this a little bit more, this is the equation for a parabola. Y is equal to ax squared plus bx plus c if we rearrange this. Now, if you haven't taken Math 20 yet, take it next semester. Hopefully, you think back to this next semester and say, hey, wait a second, I remember this. Okay, this is a parabola, and it works an awful lot like that. Y is equal to ax squared plus bx plus c. Makes sense, right? If we're going to analyze the y component, and it is a parabola, it makes sense to use the equation that is the equation for a parabola. It's going to be the most likely to work for us for the y component. Having said that, if you can make it work with some other group B equation, that's okay, because they're all valid in this situation. Now, let's point out the differences between these two problems. So far, we've looked at the similarities, the two equations. What are the differences? Well, the first difference is the velocity x component. The velocity x component in this case up here is 20 meters per second. It's all of it, right? None of it is the y component. All of it is the x component. So if it's launched at 20 meters per second horizontally, the velocity x is 20 meters per second. If it's launched at 35, then the x component of the velocity is 35, all of it. But over here, the x component is not the entire velocity. It's not 15 meters per second. We would have to take that off to the side, find the x component, and we would find that it would be 15 cosine 50 degrees. Right, cosine 50 degrees is equal to the x component over 15. So whatever 15 cos 50 is what our x component would be. We have to take the number directly off of the data for this one, and we have to find the x component of the number directly off of the data in this one. Now, the second difference here is the y velocity. The second difference is the y velocity. The initial y velocity here is 0. The initial velocity y component here is 0 because, I don't like that actually. Let's change the color of that. Actually, let's just change the shape. Let's do this. Let's say the initial y velocity is 0 because it's all launched horizontal. You launch it at 10 meters per second off of the horizontal roof, then the x component will be 10, the y component will be 0. If you launch it at 20, the x component will be 20, and the y component will be 0. If you launch it at 45, the x component will be 45, and the y component will be 0. Every single time when we launch it horizontally off of a roof like that, the y component will be 0. Now, the y component of the velocity over here isn't 0. Right? We've got a y component to that 15 meters per second. So we can't just say it's 0. Rather, for this one, for the one that's launched at an angle here, we're going to say it's 15 sine 50 degrees. Take it off to the side, find the x component using cosine, find the y component using sine, and this is what we end up getting, 15 sine 50 degrees. Finally, the last difference here is the y displacement. The y displacement in this case, over here in the first problem here, would be negative 40. Negative because it ends up down below where it started. 40 because, well, that's the height of the building and falls 40 meters till it reaches the ground. Over here, the y displacement is not negative 40 or not negative anything. If it lands on the ground and it started on the ground, or whatever, if it lands wherever it started vertically, then the vertical displacement is 0 meters. So you can see the three differences here, right? The x velocity is different. You can see the y velocity initial is different. And you can see the y displacement is different. Everything else is essentially the same. Numbers might be different, but the way you look at it is exactly the same. Now, once you recognize what's what, what's the strategy? Brute force, right? We don't have a strategy really. Okay, it's just sub in whatever numbers you got and get something. Okay, if you're looking for the time, don't worry about it. Just sub in your numbers and get whatever. If you're looking for the x displacement, don't worry about it. Just sub in your numbers and get whatever. And if you're lucky, you might happen to get whatever you're looking for right away, but not because you're planning it that way, just because you got lucky. If you don't get what you're looking for right away, that's okay. Just take what you just got and then sub it into the other equation and try to find what you're looking for. Got it? All right. You had 3 questions for homework last night. They were all involving the second type of problem here where we were launching the ball at an angle here. The questions that we had last night were worksheet number 9, questions 5, 6, and 7. Let me give you some answers to those 3 questions right now, and then we'll just choose which question or questions that we want to go over as a class here, as practice. Question 5A. 5A, I got 2.0 seconds to 2 digits and 35 meters. 6A, I got 1.8 seconds. Again, that's rounded to 2 digits. 8.8 meters. That's also rounded to 2 digits. And I think I gave you the answers to these yesterday, didn't I? Okay. 7.5 meters for this one. I want to go over question number 6. Okay, I want to go over number 6. If we need anything else going over, we will as well. But we'll go over that one together for sure in a moment here. 7, I got 3.9 seconds for A. For B, I got 90 meters. And for C, I got 19 meters. Okay, I want to go over number 6. Will that take care of it for us, or do we need to go over another question as well besides number 6? Or should we go over number 6 and then see where we're at? Okay, let's do number 6. If you need another one gone over besides number 6, then we can absolutely do that. Let's try number 6 first, though, okay? Let me just copy this, make a copy of it so that I got a little bit more space. And then let's tackle it here. The question says, a ball is thrown from a height of 2 meters at an angle of 60 degrees at 10 meters per second. The ball is caught by another person at a height of 2 meters. So in other words, you're throwing it not from ground level, you're throwing it from basically just above your head, right? But then the other person catches it right here just above their head. So it ends up being caught at the same level as it was thrown at, right? That's not any different than if the ball was kicked from ground level and landed on ground level. The vertical displacement there is 0. It starts at 2 meters, it ends at 2 meters. It doesn't matter where it starts and ends, as long as it starts and ends at the same place, the vertical displacement is 0. Okay, we want to find the time of flight, how far downfield the ball lands, and the height of the ball at 0.8 seconds. We're not really going to have much of a strategy here other than draw the diagram and write down the equations that we know always apply, and then just brute force sub in numbers and see what we get. We're not necessarily trying to find A in particular or B in particular. That'll just happen as we work through this. So let's draw a picture here. Here's our object here, the ball that's thrown from 2 meters. I'm just going to draw it like this. Okay, this is already 2 meters above the ground, so is this. It's thrown at 60 degrees and 10 meters per second. We want to find the time of flight, how far downfield, and the height of the ball at 0.8 seconds. Let's take that 60-degree angle, 10 meters per second off to the side here. Get rid of it, because we don't like it. And this is what we do. This is what we did for the quiz yesterday on those problems where we were adding vectors together. We had a funny angle. We took it off to the side. We got rid of it. We solved for the x component, and we solved for the y component. No different here. It's going to happen in Physics 30 too. We just wrote a unit test last Tuesday in Physics 30 on something called momentum and conservation of momentum. You don't know what that is right now, but you could actually right now do part of those problems because some of those problems involved funny angles that we had to get rid of using the same technique as we do here. Let's say cosine 60 degrees is equal to x over 10 adjacent over hypotenuse. X is 10 cosine 60. I think that works out to be 8.6603 meters per second. And the y component, no, it isn't. That's 5, isn't it? 10 cos 60 is 5, isn't it? And then we're going to say sine 60 is equal to opposite, or the y component, over the hypotenuse. 10 sine 60 is 8.6603 meters per second. Let's box that off because that's what we do. And then if you want to, and I don't know, I find this valuable to do this, just replace that initial vector, which really does describe, it helps you to visualize the actual picture better, what we had, but this helps us to visualize the components better. 5 meters per second this way, and 8.66 meters per second this way. Well, then we do our thing with our x and y components. Notice I haven't once referred to, since I read the question, what I'm actually looking for in the question. That doesn't concern me right now. I'm just solving the problem. I'll get what I get. And by the time I'm done, I'll have solved for the time of flight and how far downfield the ball lands. The x component v is equal to delta d over delta t, and the y component d is equal to vit plus 1/2 a t squared. What's the x component of the velocity here? Okay, what's the x component, Brad, what's the x component of the velocity here? Not 10 meters per second, right? That's your hint. It's not 10. Yeah, good. It's 5.0 meters per second. We sub in the x component as 5. We don't know the horizontal displacement. We don't know the time. So far this hasn't been overly helpful to me. That's okay. Okay, no worries. Claire, can you tell me what the y displacement is when it starts at 2 meters above the ground and ends at 2 meters above the ground? 0. Good. It ends up vertically where it started, right? So we say the y displacement is 0. The horizontal isn't. Try to find that actually in question B, but the y component is. Grant, can you tell me what the initial velocity is, y component?
8.66.
Good. 8.6603 meters per second. And it's the y component right here of that 10 meters per second. Remember, that 10 is dead. We're never going to use that 10 meters per second at 60 degrees again. We completely replaced it with a 5 and an 8.66. So 8.6603 times time plus 1/2 of neg 9.81 times time squared. Now, I'll simplify this just a little bit in my next step. 0 is equal to 8.6603 t. Subtract half of neg 9.81. It's 4.905. You don't need to memorize that. Like, I've got that number memorized in my head because I've seen it so many times. But you can, on your calculator, go 0.5 times 9.81, right? It's a negative because, or we're subtracting because it was neg 9.81. Now, this is the tricky thing from yesterday, the most challenging algebra that we've done so far this year. Solving for t here. What did we do? What did we do when it appears in two places here? Yeah, we divide everything by t. If we divide 0 by t, we get 0. If we divide 8.6603 t by t, the t's cancel, and we get 8.6603. If we divide t squared, 4.905 t squared divided by t, then one of the t's cancels on the top and bottom, and we're left with 4.905 t. You notice that if displacement vertical wasn't 0, we couldn't do that. Because we can't say, like if the vertical displacement was 7, let's say, we couldn't say 7 divided by t and it just disappears. 0 divided by t is 0, but 7 divided by t isn't. If the vertical displacement wasn't 0, and the good news is for us in Physics 20, it will always be 0 in these problems. But if it wasn't, and it won't be necessarily if you take a course in physics in university, if it wasn't, then you would need the quadratic equation. How many people know what I'm talking about, the quadratic equation? You need the quadratic equation to solve that problem if the displacement wasn't 0. You didn't need it for this problem just because of the nature of this problem. But the right side here, those ones launched at an angle, the vertical displacement needs to be 0, otherwise we need that quadratic equation. You're never going to have a problem in Physics 30 where you need to use the in Physics 20, where you need to use the quadratic equation, because not all of you have done it yet, right? It's not fair to make you use it when not all of you have learned it in math class. Okay, so what I want to do now is take the 8.66 over to the other side by subtracting. It becomes negative 8.6603 equals negative 4.905, and t that is. And we solve for t there. Negative 8 divided by negative 4, it gives me a value for t of 1.76560 seconds. Or rounded to 2 digits, it would be 1.8 seconds. Bless you. Look at that, I just solved for A. I wasn't even trying to find for A, solve for A. I just did. It just happened. Now, does anybody know why I wrote down the unrounded number for time there? Why did I keep, Judith, why did I keep the unrounded number there, even though question A asked me for the time and it's going to round it to 2 digits? Why did I keep the unrounded number 1.76560? Yeah, good. Just in case, look, I got 2 more questions, right? I just solved for A. I got two more questions. Even if you don't recognize right now that you're going to use it, you might use it, right? So let's keep that unrounded number just in case. And sure enough, I do end up using it, right? 5.0 meters per second is equal to delta D over the unrounded time. Solve for delta D there. Take the 1.7 up by multiplying. 5 times 1.7 gives me 8.8 meters. Okay, I just solved for B. In question C, I'm going to find the height at 0.8 seconds. I'm going to solve for the y component here. I'm looking for height. That would be a displacement, right? So let's solve for the displacement here using VIT plus 1/2 AT squared at 0.8 seconds. The difference between the y component that I'm doing now and the y component I just did is that I know the time and I don't know the displacement. So I'm going to say VI. Well, VI is still 8.6603. That's the y component of the 10. The time is 0.8 seconds. So 8.66 times 0.8 plus 1/2 times negative 9.81 times 0.8 squared. Let's do that on the calculator here. Oh, I think my calculator's expired. Good. Good news, not expired. Okay. So let's do this here. Let's say 8.6603 times 0.8. Let's just press enter there. That first term, we have a number. And then let's add to that number brackets 0.5 times negative 9.81 times 0.8 squared. Okay, you see the keystrokes there? Don't square the whole thing, just square the 0.8. When I do that, I get a value of 3.78. Is that right? That's not what I have. That's not what I have on my answer key. I am getting 3.78904 meters. I'm mistaken my answer key. Question? No. But that's still not the answer. That's the vertical displacement. But what are we looking for? The height of the ball at 0.8 seconds. What's the height of the ball at 0.8 seconds? Anyone? Did we not start from 2 meters high? This is the displacement, 3.78, above the starting point. So what's my height at 0.8 seconds? Well, this is my displacement at 0.8 seconds, but my height at 0.8 seconds is 5.8 meters. Does that make sense? That's a tricky one, isn't it? Usually I don't give you questions like that on tests. Like to solve for the vertical displacement at 0.8 seconds, sure, like that's fair game. But to kind of almost trick you into finding the vertical height at that point where you have to add the initial height, I'm probably not going to do that to you on a test. One more quick little thing. You weren't asked to solve for this with this question, but let's pretend you were for a second. How would you find the maximum height? How would you find the max height for this? Yep. Yeah. You're analyzing the y component. It's always the y component for max height because height is a y-axis thing. VF squared is equal to VI squared plus 2AD. And we talked about this when we reviewed it at the beginning of class, right? The vertical velocity when it reaches the top, in other words, when it reaches the max height, the vertical is 0. So sub in 0 for this. And VI would be, what, 8.6603? A would be neg 9.81. And you'd be solving for the displacement here. Now remember, in this question, it would be tricky because the displacement you get there wouldn't actually be the max height. That would be the displacement above the 2 meter starting point, right? So you'd have to add that to the 2 meters. But like I said, on a test, I'm probably not going to do that to you. I may very well ask you for max height, but not for the height. Sorry, but not when there was an initial height of 2 meters. You guys feel okay about that? Do you need to go over another one, or are we good? You good? All right. That's the unit. Guys, I will refer you to the physics 20 and 12 pages, that review document that I posted on Google Classroom by the first day of school. I don't know how many of you guys printed that off, but you either have it in your binder or you have it available on Google Classroom. Just an outline of the course. We started, if you've ever looked at that, we started on page 2, topic 11. The first 10 topics on page 1 are just general stuff that we cover throughout the course. So it's not like specific objectives that we do. We do number 1, then number 2, number 3. We don't do it that way. We start at number 10, then number 11, then number 12, and so on. And then we just kind of mix in those first 10 topics as you go through the unit. If you go through that tonight and tomorrow night as you're preparing for your test, you can see that the topics that we have are topics 11 through 19. Topic 11, distance, position, displacement. Topic 12, time. Topic 13, speed and velocity. 14, position, time graphs. 15, acceleration. 16, velocity, time graphs. 17, vector addition. 18, relative motion navigation. And 19, projectile motion. There's all kinds of subtopics within each one. 13, A through F. 15, A through G, and so on. Look at those. Use it as a checklist. Do I understand what this is telling me? Do I understand this, like what this means? And then do I understand the topic that it's describing? There's 2 things, though, that I'm going to ask you to scratch off on that. You know, if you're using it as a checklist for the test, just because I sometimes add stuff that we don't have to do. And just because of few absences this semester and not wanting to get behind, I'm not going to do the extra things from this unit that we don't have to do. I've done everything that we have to do, but I'm not going to do the extra things that we don't have to do. So if you do use this as a little bit of an outline, guys, I'll ask you to scratch off 14D, okay, 14D, and I'll ask you to scratch off 18D. 14D and 18D. There's a couple questions on worksheets that you may or may not have noticed that we just didn't do, that we skipped. And that's because we didn't have to do them, and I just didn't want to get behind with a few absences this semester. So 14D and 18D, everything else you should be able to do, hopefully at least. Let's put it this way, everything else you're responsible for on your test on Thursday.